Maybe in the meantime, hey, Patrick.
Hi, Julius. Hi, everyone.
Hi, everyone. In the meantime, while we are waiting for everybody to settle, 2 more minutes, type in the chat where you're from. Just type in the city or the country. We get a bit of a feel. From Texas, Dallas, early morning, Bangladesh, Sierra Leone, Freetown, London. Where else do we have? Chile, that's early morning, huh? Duisburg, Germany, Mumbai, Irvine, all around the world, Cape Town, more folks from India, Bosnia, Herzegovina, Jordan, lots of time zones. We'll get started in a minute and a half here.
It's very obvious that you are located, Julius, in a very hot area. Well, I'm sitting in Germany here with my sweater on. It's I hardly hit 15 degrees centigrade.
Yeah,
well, you most likely are sitting in 25, right?
We are well in the 40s.
Okay,
You're still in the teens. Where else do we have? Qatar, probably also in the 40s. Jeddah, Switzerland, UK, more folks from Dubai. And it's getting hotter in Dubai, very true. UK has good representation. And I think we are, for most of the European countries, we are in between, the webinar is in between a long weekend, I understand. Netherlands probably too. Holiday tomorrow and off Friday, Bridge Day. US, early morning. Last time we had somebody from Singapore, they stayed up late. South Africa. All right, let's get started. Okay, so we will close the chat now and we will open the Q&A box. We'll talk about this in a second, but first and foremost, welcome everyone to maximizing backwash wastewater reuse with advanced ceramic membranes. I personally believe it's a super important application. I believe at some point all filtration plants, drinking water, wastewater, will treat their backwash waste. It's the right thing to do, the sensible thing to do, and we will discover today also very economical to do. We'll take you for 30 minutes through a presentation, and the presentation is split in 2 core parts. I will take part 1, which is about the application ceramic operate in, high-level backwash wastewater treatment and the market. And then Patrick, our global process expert, will take a deep dive into case studies, into actual data, into benchmarks between ceramic membranes, polymeric membranes, and sand filter for backwash wastewater. So we're really excited you're on this webinar, and we'll think we have a ton of great content. Now, you can find the Q&A button at the bottom. It looks like on the screen, you can see it circled in red, and you can ask any questions during the webinar. We will take all the questions at the end of it live. We will stay for an hour if needed. We will answer all your questions. If you can't see it, press the 3 dots. It opens a window and you can submit your questions during the webinar at any point. If you have questions you want to ask or get in touch outside this webinar, just email us at webinar@cerafiltec.com if you want to talk about opportunities or corporations or want to speak with a consultant or a technical expert. So reach out to us. We would love to connect with you. Lastly, I want to thank all our partners and our customers. Many of them are on this call for taking the journey together on this really exciting path of bringing innovation into the water space, driving and catalyzing the transformation from conventional solutions and polymeric membranes to ceramics. We're really thankful for walking that path together with you. So without further ado, let's dive right in. I want to let this graph sink in for just a minute. This chart is not about wars or conflicts. This chart is about water. And it's telling us something very, very fundamental. Water is not only a utility anymore. Water is a strategic resource. It's used for manufacturing chips. It's used to power data centers. It's used for food supply. It is powering our economy just like energy is. And the funny part is we recycle everything. We recycle plastic, we recycle steel, we recycle rocket ships, but we don't really recycle water. Only 11% of the global wastewater today is being recycled. The most valuable resource. And I think all of you in the water sector know that this is about to change. We have discussions, you have discussions with the food and beverage sector, you have discussions with the mining sector, you have discussions with semiconductor plants, all of them looking to maximize their water reuse, yearning for zero liquid discharge. And also municipal water treatment plants looking to treat the backwash waste to reuse the water. Recovery and reuse are no longer optional. They are mission critical. And this is not just for water scarce regions or developing markets. This is important for all of the regions where we are currently present in, for California, for Arizona, for Texas. Germany's aquifers are depleting. Southern Europe is in a water scarce environment now. All of the Gulf region, all of the Middle East, and the list goes on and on. Water is so important, and reusing it is mission critical. And it goes without saying, we need we need the right technology to maximize the water reuse. And this is why I'm extremely excited to share the benefits of ceramic membranes, to create awareness about this tool. And we at CERAFILTEC deeply believe that ceramic membranes are the future of global water filtration. And in contrast to polymeric membranes, they operate reliably, they are sustainable, they truly make a difference in water reuse and drinking water filtration. So if you're a plant operator or a system engineer or a system integrator, ceramic membranes can be the tool that unlocks the full potential for filtration for you. And this includes reliable operation through a robust technology without fiber breakages. This includes having a long membrane lifetime, expected 20 years, 3 to 4 times longer than polymeric membranes. Having a chemical resistant membrane, so you don't have to be worried about ppm hours when wanting to clean it. Not having to bathe them in low concentration solutions for sometimes days, hoping they can recover. You can fully recover them, even with plant upsets, even in presence of oil, even with upstream issues. And ultimately, you improve savings. You save OpEx, you have membrane lifetime savings costs, and that's where the value from ceramic membrane comes. What's counterintuitive is that ceramic membranes actually play a major role in the filtration system, in the filtration world by now. You might be surprised to hear that ceramic membranes have the same market share in the global MFUF industry as Bose has in the headphone space. Bose is a major player with 10% market share, just slightly above. Ceramic membranes is a major player in the membrane space. But more importantly is the trajectory. When CERAFILTEC was founded, only 1 to 2% was the global market share of ceramic membranes in the MFUF industry. Today, 9 years later, ceramic membranes make up 10% of that market. And in the next 10 years, it might be 20 or 30 or even more. We truly believe at CERAFILTEC that ceramic membranes will completely and entirely displace polymeric membranes over time. And this is nothing atypical. This happens across all product categories, these technology transitions. And let's use just one example, but you can pick any. The incandescent light bulb, the standard light bulb that we all know, that you have to replace every 6, 9, 12 months manually, right? Now being completely converged to LED membranes. LEDs came out early 2000s in a niche application. microelectronics, similar to ceramic membranes that started a niche application. Then they became more competitive. Consumers became aware of the total cost of ownership advantages, just like in ceramic membranes. Sustainability drivers helped propel LED adoption forward, just as what we're seeing now in the filtration world with ceramics. The performance improved, the cost improved, and today LEDs have 90–95% of the global light bulb market share. They're the dominant player. And we truly believe the same will happen to ceramic membranes, just as it happens to any other product category. So being acquainted with ceramic, building experience with ceramic as being part of the water sector is really important. Ceramics are becoming mainstream, recognized by institutions like Global Water Intelligence, and you can see here the data. Large projects way over 100 mld are not atypical anymore. There are multiple players in multiple applications, in multiple regions, building large projects. Consultants embrace the technology, large developers embrace the technology, and ceramic membranes are growing and taking market share. So where do ceramic membranes really play? A quick overview. On the wastewater side, ceramics are used in MBRs, in tertiary treatment, and what we talk about today, backwash, wastewater. Ceramic membranes are used in surface water, in groundwater, in RO pretreatment, specifically seawater and brackish water. They're used in processed water like produced water, refineries, in harsh feed waters, as you can find in semiconductors, or with hot water, scrubber, battery recycling. And they're used in greenfield projects, and they're used to directly replace polymeric membranes, hollow fiber or flat sheet. They're used for process combinations, for example, with advanced oxidation combined with direct filtration. Or they're used in process consolidation, replacing settlers, MMF and UF to one single stage. And in general, you can say the more difficult the feed water, the greater the value ceramic delivers to the end customer, to the integrator, to the consultant. If you have multiple treatment steps required to achieve the filtered water quality, or if you have fluctuating feed water or troubles with polymeric membranes or sand filters, ceramic membranes come to shine. So let's jump to backwash wastewater. Why do we treat backwash wastewater? Why don't we simply use a settler and take the clear water phase to the front of the drinking water plant, like it's the case in many, many projects? And there are three major reasons. Number one, safety. Settlers don't solve the problem, they actually incubate it. Settlers are large holding ponds or with long retention time tanks that incubate parasites, Giardia crypto, the warm eggs that are spewed out from the sand filter, flow to the clarifier, to the settler. Algae grows, bacteria grows, and ultimately all of that mix flows to the front of the drinking water plant. In the process to try to contain that, you're chlorinating, you're creating carcinogenic THMs, and then the carcinogenics and the pathogens go all into the drinking water plant. That's not what we want. What we want is a physical membrane barrier that rejects all of these pathogens and that create a treatment process that doesn't require chlorination to prevent the THMs. Number two, when it comes to footprint, less is more. Footprint is expensive, especially in the private sector, and some plants simply don't have the available space. A clarifier is order magnitude 5 to 10 times larger than a UF treatment system, and it makes sense to save that space. And lastly, reclaim it, don't lose it. As we discussed, water scarcity is ubiquitous. We need to reuse the water, ideally all of it. And ceramic membranes can capture up to 99.9% recovery rate. We don't need polymers, we can directly filtrate. And this is important for all of the treatment plants that have withdrawal limits, or in Europe, in particular Germany, where you have finite groundwater that's depleting, and you reduce the high sludge costs that you have by not capturing the full recovery rate. So that's really why we want and should treat with membranes backwash wastewater. And Patrick will take you now through why ceramic membranes is the right choice to do that. Patrick, I'll hand it over to you.
Okay, thanks a lot, Julius. And I'm pretty glad, first of all, welcome to everybody. And I'm pretty glad that I have the chance to introduce now the fantastic suitability of our technology to that specific application. And to start with, first I would like to clarify when we talk about backwash wastewater, what we actually talk about. And here, two major applications coming into my mind, and that's also where the more major experience is based on is on a surface water treatment. That means there is a first filtration step, treating water from rivers, lakes, dams, whatever, by sand filtration, ultrafiltration. And what was also coming up in the last years was the groundwater treatment, where sand filters are removing mainly ferric or manganese or both by sand filtration, maybe previous oxidation. And those both wastewater types are what we would like to focus on. Nevertheless, there are also other filtration processes, other applications where backwash filter water is created. Also, we are in here, but nevertheless, let's focus on this two now for the first step. So looking closer into surface water, for example, you know about the characteristics and the flow scheme. So typically what you always need as a pre-treatment for the filtration is an addition of a coagulation. In the recent years, it was also getting more and more popular to add an optional powder activated carbon dosing to be prepared for accidents or emergency cases. Then depending on the feed water quality, you might have a clarifier followed then by the actual filtration step with in older plants, sand filtration, in modern plants, more with ultrafiltration. The second, and here the water, the characteristic of this water is typically, high organics. You have color, you mix, you have a fluctuation in TSS, seasonal most likely. There is always coagulant in the process, and you also typically deal with organic trace compounds. And in the future, it's getting more and more common to deal with that by powder activated carbon dosing. While in well water, this scheme looks a little bit more simple. We have just here then the well, and as the major subject is to remove the ferric, it's sometimes oxidation step which is included, and then followed by multimedia or sand filter to remove then the ferric and filter the manganese oxides out of the water. Characteristic here is mainly then, for this purpose, high ferric and manganese concentration, lower in organics, and also low in TSS from the well as such. If you're going now into the process scheme for the second stage filtration, often these designs, especially when you go to surface water, are designed in the first stage with a 90% recovery rate, followed then by wastewater treatment step, which is already existing, of course. Yeah, it's not new. It's already, I think, in place for more than 10 years, I think, in many countries. And here you see now on the left side, 10% of the water from the first stage is considered as wastewater. Concentration factor here, marked as CF, is 10, going then to a second stage to treat then the wastewater. This is typically also, depending on the feed water quality, a two-stage system. And depending on the TSS, it requires then a clarifier, a sedimentation or a flotation, followed then by an additional filtration step, depending, of course, on the purpose and on the reuse requirements. In total, I would say these systems can reach then something like in the range or above, slightly above 98% of recovery rate. Please keep that number in mind. We come back to that later. And in the end, on the sludge side, you see then with the concentration factor of 100, the drain can go to the drain or actually also to further treatment with centrifuges or any other sludge treatment. So coming up now, why ceramic, or what is now the role of ceramic actually? And first of all, I would like to introduce a little bit closer the ceramic membrane, what we talk about here. So as a membrane material, it's the one and only for ceramic is aluminum oxide, as this gives you the best and most narrow pore size distribution, It's an asymmetric membrane. We can provide several certificates as well, and the cutoff is always below 100 nanometer here too. It's a submerged technology, submerged out infiltration, and strong characteristic here is that the TSS in the feed water can handle continuously up to, or even more, 1000 ppm continuously. Typical flux ranges when we talk about standard applications, so when you're familiar with membranes, you know that this is a very vague number here, but I would say 100 to 350, depending on temperature and water composition as well. Typically, we operate at a recovery rate of plus 95% actually. What is also unique is actually, I think, most of the process combinations we can offer here, which are also, related also to a higher TSS already. For example, we easily can operate with CERAFILTEC's active cake layer process, which is a powder-activated carbon dosing to create a nice layer on the membrane. We can add bentonite, coagulation, of course, and we continuously can accept ozonation actually without impacting the lifetime, which is plus 20 years. So with that module, with the ceramic membrane is now put into a module, which is out of Noril, which is a fiber reinforced plastic, injection molded, all corrosion free actually, also the screws and so-called keys at that element. We combine those plates to reach 6 square meter per module. With that, we stack them together to a so-called tower, which is then can reach up to 16 modules in a tower, means 96 square meter per tower. And those towers we then put into a line, and we can combine them in parallel also to create a rack or a train, however you want to call that. So you see highest modularity also to ensure the possibility to replace existing systems and to fit in all tanks.
Patrick, very quick comment before you talk about this. Can you turn up the volume easily on your side? It seems to be a bit low and people are commenting. Not sure if it's easy.
I have no idea how I should do that.
Long. If not, just speak up a little bit, I suppose. Scream into the microphone. Okay. Just speak a little bit louder.
Okay, I speak louder. I'm not sure how I can do that here.
No worries.
It's all maxed out. Sorry for that. So looking at the filtration process, it's what you have expected already. It's an out-to-in filtration. That means we have a vacuum pressure on the filtrate side, sucking the water into the membranes. And with that, we create nice, shaping up a nice fouling there on the membranes, which will be then backwashed with a higher flux rate than during filtration. So in the next slide, I show you a little bit more how that is working. And you can see here a video which is showing us now a tank where we have a special split cutted module. And you see here now at the tank filled with ferric hydroxide. I think it's in range of 3 to 5 grams per liter, so very high concentration. We're filtrating the water, we're recycling it back to the tank, and you will see then filtration and then the backwash. And that is very impressive. And you will see once we start the video how this homogeneous layer will shape up on the membranes. And you see also the nice backwash effect and also how the air scoring can clean it. And that is a major advantage of this technology and of this product as well, as you don't have any hydraulic pressure drops during the filtration process. You will see now easily, and countdown is coming, and here is now the backwash, how releasing it is to see and to watch that backwash. You see the fouling layer just falls off. Isn't that a great feeling? I always get chicken skin when I see that. And now with the air scoring, you can really control the fouling completely, complete whitish membrane. That's typically the process. And you see as well that, with the strength of the air as well, it's not really a mechanical stress for the membrane, which is completely different from the polymerics where you need always a mechanical stress as well, which is also impacting the lifetime. So in the next slide, maybe we can stop that one. I can demo a little bit, what another advantages of the submerged technology which we have here, especially for that application. It is actually an advantage to combine the sedimentation and the filtration in one tank, right? So what you can do then is not to drain the tank during every backwash, what is relatively typical. You can control actually the TSS concentration in your tank by removing just the already sedimented sludge in that tank. With that, you can achieve incredible recovery rates, right? So it means you don't homogenize with the air. You just let the particles sink down during the filtration process. Next, please. So this results now in another numbers now for that scheme. So we keep going on now with the first stage of having a 90% recovery plant. That means still 10% reaching to the second stage. But you see already now we just have a single stage into the backwash wastewater treatment. And with that, maybe you can click the button. You see that we can highlight some numbers here. With that, we can reach up to 99% recovery rate into the filtration process. That means in the end, we reach a concentration factor of up to 1,000, and the overall recovery rate of the system will end at 99.9%. So then in such a case, it's even, questionable if you need further sludge treatment, because you reach already most likely up to 10% or something. But nevertheless, you see the big advantages here. You have a single treatment step in the second stage with a maximum recovery rate, far smaller sludge treatment, and also less chemicals for the sludge thickening process as well, right? So many advantages here. And with that, maybe we can go to the next slide. Better late than never. So to highlight again those numbers, keep them in mind and compare them to the others one. So showing you now some real life actually experiences. So I want to start with a funded project which was happening in the last, I think it was 2 years ongoing, and I think concluded last year. It was called FITWAS, where it was also investigated in a comparison of different membrane systems or technologies to actually treat the wastewater from sand filters which are in the groundwater application to remove ferric and manganese. This was mainly targeting the northern region of Germany, as also there is, they have to deal with water scarcity. Although you have the feeling whenever you go there, it's raining. But nevertheless, the aquifers are suffering already. So therefore it is investigated in that. And as a result, maybe we can just quickly go to the next slide, and we see already the most important number here is if you compare it now to 2 different polymeric pressurized systems, the recovery rate of the ceramic membrane was above 99% compared to 85 and 89 of the polymeric system. So 10 to 14 times less waste which is generated and more concentrated sludge, higher recovery rate. Very impressive result for the ceramic membrane. So the second one, and here I would like to thank WETENS and Logisticon for supporting with pictures and information. This was an 80 cubic meter per day application, also in a groundwater treatment in the Netherlands. Also there, the major purpose of the treatment was to remove ferric from the groundwater, from the wells, by conventional sand or media filtration. The recovery rate here of the sand filter system was in, I think, 95%, so 5% reaching then the second stage. The design of the plant has been made at 100 liters per square meter an hour. And you see here on the right side in the picture, there are 2 trains actually, each in total 12 towers and 132 modules of CERAFILTEC. Impressing maybe settings here, if you're familiar with ceramic membranes, you might notice 1 hypochlorite cleaning in 2 weeks. So it's pretty seldom actually, a very low cleaning frequency. And citric acid actually, as of now, it was not yet applied. We have considered as per design 1 to 2 per year, but as of now, it's already in operation now in more than 6 months. No cleaning has been required, and design recovery was 95%. We are continuously supporting and optimizing the operation. So currently, we just have received the message that we are reaching already 97%. Going to the next slide, where we have also some information from the water qualities. Actually, you can imagine the well water is low in turbidity, low in TSS, of course. There is a high content of 8 milligrams per liter of ferric. which ending up then at 160 milligrams in the feed to the UF. And you see also the TSS continuously to the feed of the UF is 1000, which results in 20 grams per liter in the drain of the ultrafiltration plant. The filtrate quality is typical for ultrafiltration, actually, turbidity below 0.1, TSS below 1, so absolutely in range. And I really love that project because it's a replacement of a polymeric submerged system, right? Before, there was a hollow fiber system installed, and the customer was not very satisfied with the performance, actually. So therefore, it was replaced with ceramic. You see the parameters here. You know, we on the same footprint, CERAFILTEC can operate at 100 LMH in the same application. Then the polymeric membranes was going with 25. Recovery rates 15% higher, 95% versus 80. And very significant is the time for when the aeration was working. So as you can imagine, the hollow fiber membranes needs to be always, you know, moving, and you know they need this for preventing the membranes from fouling and from clogging. Actually, CERAFILTEC only needs it for the backwash. So 25 times less aeration time. That means also a high savings in energy, higher recovery. Filtrate quality most likely was good for the submerged polymeric system in the very beginning, but as it needs to be replaced after 5 years, it was not, because it was not suitable anymore. It was not good looking anymore. It was because the water quality was not fulfilling the requirements anymore. So therefore, it needs to be replaced exactly after 4.6 years or something. So we expect, of course, lifetime for the ceramic more than 20 years. Very impressive, I think. And it also, you know, it was so nice because actually nothing needs to be changed from the equipment side. So it was really almost like changing a tire at the car. Of course, our customer would say, no, it was not that easy because, of course, they need to change pipings and stuff. But blowers, pumps, chemical equipment all remained the same. Tanks, it was just like interconnecting pipework. So very smooth, actually, very fast, and some modifications in the process, of course, but nothing serious, actually. So then coming maybe to a bit of a different application, not well water, but also not surface water. It's now in a zoo in Europe, where there was a pool for elephants, actually. And this was originally equipped still with a sand filter, but the backwash water of the sand filter was treated by an in-out polymeric membrane. And this was suffering a lot. And you can imagine that is, I think, you know, the biggest challenge, I think, in this application is that you cannot really rely on the feed water quality, right? The turbidity goes up and down, and you know the elephants are not really well trained to leave the pool once they need to go to the toilet or so. The pool will experience accumulated sludge. The TSS will increase. We have peaks going up and down, and it's very difficult to control what is then coming to the second stage, ultrafiltration. And with that, you know, the experience were very bad. It was replaced, and now actually it is working at 233 LMH with almost no chemical cleaning, and also with high recovery rate and zero hassle. And that is, I think, also a key advantage of that technology, right? You are in this area, you're not dealing with water experts. You have no operators which are well trained and have all this engineering education on water treatment. So the system just needs to simply ensure that the animals having a nice environment, and that's what the ceramic CERAFILTEC membrane stands for: reliability and process sustainability. Then last but not least, going to introduce you a surface water treatment in North Africa. You can imagine their water scarcity is, of course, a big topic over there. So every drop counts, and 10% losses of the sand filler is a lot. So therefore, they are looking now into a second stage UF of this 70 MLD drinking water plant. And also there we did pilot, and you see the results on the next slide. So here it was flux rate of 100 LMH with a really reliable operation, not too many CEVs actually. The backwash was very effective. recovery was reached 95%, but easily not really optimized. Actually, it was a short pilot test only. And on the next slide, also we see then the water quality parameters. Also here, the continuous feed was in the range of 1,000, 1,200 milligrams per liter. The drain of the UF, the sludge, was then 24 grams per liter. So significant was increase in concentration factor. And filtrate quality, of course, in the range of ultrafiltration. So below 0.1 NTU, below 1 STSS. So to summarize, maybe, so if you, I hope I created that, to transfer this message properly. You know, very significant is really the maxing out of recovery rate, right? If you see, we reach up to 99.9%, and that's especially when you go with the with this special process to just, you know, drain the sludge and not the whole tank. You can really max that completely up, and that is, I think, completely unique and absolutely super suitable for that application. Number two, in my opinion, is even more important that, you know, this reliable operation, even during process hiccups. It's just an insurance policy for the operator. And, you know, I mentioned that before in the zoo, but it's also happening when you, especially when you have, for example, powder activated carbon, right? It's maybe the homogenization in the tank is not working properly. You have accumulation in tanks or pipes, and suddenly a huge, let's say, cloud of TSS is reaching the membranes, but the ceramic membranes from CERAFILTEC, they don't care, actually. They love to digest TSS. It's food for them, right? It's not a threat then for other polymeric membranes. It is really something which don't even tickle them. So that makes it so safe and so, yeah, such a no-brainer, actually, for this application. And then as a third point, it's a single step process, right? It combines the filtration with sedimentation. You minimize the footprint, but also it's minimizing your efforts for controlling the process, as you only have one treatment step beside two maybe. And of course, it's also then cost effective as you have less investment here too, and you need less footprint. So I think that was the conclusion here too. Julius, if there's nothing else to say, we can jump over.
Yeah,
to
thank you,
Q&A,
Patrick,
right?
for taking this deep dive into the case studies. And I think the data speaks for itself. And obviously today was all about backwash wastewater treatment. Ceramic membrane works in many applications. So do contact us if you have any questions outside backwash waste or just want to get in touch with us. But I'm really passionate about this particular application. I think there's a lot of opportunity. The entire space of water reuse is so important, as we discussed in the beginning of the presentation. And then maybe a last comment, we do have pilot units, we have suitcase units, we call them, because they're essentially the size of a suitcase, and we can take them to your plant, to your customers, to your partners, and we come to you together and actually trial at your plant to show the filtration flux rate, the TMP, the filtered water quality very easily in one day. So if any of those requests are there or opportunities, don't hesitate to contact us at webinar@cerafiltec.com. Good, we got a number of questions in as well. And as promised, we'll go through it one by one and cover them. I'm just opening it, I'm reading out loud. And perhaps Patrick, especially the technical ones, you can explain, and some of them I can take on the commercial side. What is the typical flux rate for wastewater with TSS 20 milligrams per liter, hardness 150, and TDS 2,500?
You know, it's always difficult to give a clear answer on that, especially without knowing about the organics in the water, or COD or DOC. But I would say, you know, something in the range of 100 to 150 LMH, to make it short.
Excellent. Good. And then we have an inquiry about a specific project for a specific region. It's one of our projects over 100 MLD in India. What's the status there? I think we are operational for about 50%. The remaining 50% is still in commissioning, but we're happy to talk more in details if it's helpful. Then there was the comment about the voice being low. We hope to address that. I hope everybody could hear as well. Next question, when the homogeneous layer, this is to the backwash cross-section view, drops off, does it typically stay coagulated together, I assume agglomerated together, or does it redisperse into the solution?
Depends a bit, especially in this application. It's nice that it's sedimentating very well and will sink down to the floor to the tank floor pretty good actually. So it stays coagulated, most likely not in an undefined sizing, but it does not completely redisperse in the solution.
Then can we have a copy of this webinar? We do plan to put it on YouTube after the session. Can you let us know the cost difference between your ceramic versus PES or PVDF, UF? You know what I think is a good proxy. You saw earlier the case study that Patrick presented on where hollow fibers were installed. And I think on a CapEx basis, both membranes are very close together. Maybe this is the best way to describe it, but obviously on an operational basis, I wouldn't be surprised if ceramic membranes save 70%, if not more, on OpEx, with having 24 times less aeration needs and 4 or 5 times longer membrane lifetime. So you're going to have substantial total cost of ownership savings with the same CapEx. We have seen that cost of ceramic is higher compared to UF. You know, it really depends on the application. If ceramic membranes, I can tell you, can also be way lower in CapEx. If we operate, for example, in groundwater with 400 LMH, and polymeric membranes are designed with 60, 70 LMH. So it really depends on the flux design. And then oftentimes the comparison shouldn't be membrane to membrane, but what is the project CapEx in project A with polymeric membranes to what is the project CapEx to a project with ceramic membranes? So by way of example, we have a number of projects where ceramic membranes is considered instead of the settler, the MMF and the pressurized UF. Then comparing the ceramic membrane to just the UF is just not the right comparison. So it's really important we look at what are we actually trying to solve? Are we trying to solve for CapEx? Are we trying to solve for OpEx? Are we consolidating treatment steps? Are we reducing headaches? Are we benefiting from having a more reliable operation? So it's always, there's no one size fits all, right? We have to look at it project by project. And I think it became a bit more clear on this webinar where really the advantages are for ceramic membranes. I hope that answers it. What is the oldest ceramic system still in use? Are there units that have actually been running for 20 years? Is that a future that has not yet occurred? I'm sure there are projects running over 20 years. We have experience with a couple of projects that are getting close to it. We have one plant that our team installed 14 years ago. It's actually in Saudi. And I can tell you that the ceramic membranes in this project are exactly today as they were on the day we installed it. And there hasn't been a performance decay. I don't think they did a single maintenance on these membranes in the 14 years, and they might operate for another 30 years. So it's hard to predict, but from all signals and indications and performance we see, the ceramic membranes might far outlast the 20 years actually. Can you comment on the brittleness of these membranes? For instance, if one of these plates located inside one of the module breaks, then isn't that a hassle for the client to take everything out and replace only that bit? Patrick, can you comment on that?
Okay, first of all, you know, the membranes are not brittle at all, right? That's why also I forgot about to mention that when I introduced the technology, aluminum oxide, you know, is far more, the flexibility is far higher than from silicon carbide, for example. That's why we're also making use of this material. And typically, you know, it is not breaking. That is the big advantage. So what can happen actually, the risky moment is the installation. So you sometimes experience that somebody is throwing a screwdriver from the top of a tank or a drilling machine, and the guy who is actually installing does not catch it. That can be then, of course, you know, a problem if the membranes are not protected during installation and if our recommendations are not followed. But typically, this is just not the case, right? You don't need to work with maintenance team to repair and everything, which is typically for polymeric membranes. Here, it is a complete, it's really a strong accident which needs to be happen. And then, yes, it is a hassle to replace it. It is possible to replace it. And with the modular system, I mean, typically, you know, submerged systems are equipped with cranes and so on. It's also possible, right? But as I said, right, not something which happens for your daily routine and your daily business.
Thanks, Patrick. What is the effect of chlorine? I think the question goes on as to what happens when we backwash. Where does that stuff go? Do we need polymers? And don't we create THMs as well if we run a CEB with chlorine? That's how I interpret the question.
Yeah, that is, of course, this is happening. I mean, that is something, but mainly also accepted in let's say, in the most of the applications. Also, polymeric membranes need to use hypochlorite for the cleaning, especially the PVDF membranes. So it is very well accepted. If it's environmentally not allowed or not approved, actually, there are also alternatives for that. Yeah, there's also our ceramic membranes can be cleaned with a high pH value of 12, followed by a pH of 2. This is also possible. In many applications, it is maybe also a combination of both. It depends, but it's nothing always uncommon, I would say, in membrane technology.
Yeah, I also think all of that stuff essentially goes then into wastewater. Doesn't go to the front of the plant to contaminate further feed water. It goes to sludge processing.
Yeah, that is, I mean, the return water is actually, you know, there is no chlorine at all actually. After the cleaning, it's flushed and rinsed, typically followed by an acid cleaning, and then there is almost nothing in the filtrate. It's all go to the wastewater actually, and that's why typically there is also then an additional wastewater treatment, or the water goes to the wastewater treatment plant.
Okay, then the next question is about a person in Sub-Saharan Africa looking to particularly use a project in surface water. I'd like to know, if we were to install the system, would any additional filtration be required to ensure the river water is safe and suitable for drinking water? So in other words, can we produce drinking water quality in contaminated feed waters?
Yes.
Maybe the answer is we have NSF 419.
Yes.
With a log removal of 6.2 of cryptosporidium as an indication for bacterial removal. So we are effectively removing 99.9999% of all bacteria, and it should be safe to drink.
Absolutely.
Can it be possible to reduce operational costs? Can it be possible to expand on the reduction of operational costs? How is that achieved compared with conventional technologies when it comes to surface water, where turbidity and organics are the main parameters to remove? Maybe I can address a couple of commercial parts, and then Patrick, you can address further.
Sure.
When it comes to comparing to conventional polymeric membranes, let's put it this way, the OpEx is driven predominantly by, well, the filtration flow pressure is pretty low, and it's the same there. On the chemical needs is similar, but the key difference is aeration and lifetime. And especially in backwash wastewater, we have a lot less aeration. In normal operation, we have also less aeration, and that drives a substantial part of the OpEx. And then with a much longer membrane lifetime, we typically achieve a lot lower membrane lifetime costs. Maybe Patrick, if you can expand a little bit on it, but I think that covers part of the OpEx.
That covers it very well, actually. I mean, if you if you talk about conventional technologies, I guess you compare also to sand filtration. And then you have to, you know, it's of course a huge difference in filtrate quality. What you achieve with the membrane technology, you have a bacteria-free, a particle-free water, while in sand filtration you have to most likely cover with the additional pre-treatment. You need polymer dosing. You need also coagulation for the pre-treatment. It's difficult to compare one by one, actually, without knowing the project requirements. And of course, you know how it is in membrane technology. You have to pay the price actually for this particle-free and bacteria-free filtrate quality as well, right? And so you need cleaning chemicals. You need also coagulation, but not to ensure the filtrate quality. There's also a key differentiator to conventional technology. There you need the coagulant to ensure that your turbidity in the effluent of the sand filter is in range, while the membrane always has the same turbidity, which is below 0.1, whatever comes in the feed water, without any further chemical dosing. Here you need more the chemicals or the coagulant dosing actually to remove dissolved organics, as you mentioned already, that this is the major target of surface water treatment, and to stabilize the process when you have seen with this nice fouling layer. But yeah, it needs to be compared case by case, and difficult to, if you look at the filtrate quality, to have a one-by-one comparison.
Thanks, Patrick. And if the backwash waste of the sand filter contains flocculant, anionic or cationic, how this would affect the performance of the ceramic membranes?
Is there the third person who can answer? No, I'm kidding. Yeah, definitely a very good question, actually. I mean, you know, the anionic or any polymer can foul membranes as such, yeah, ceramics, polymerics, and so on. So as long as these polymers are, for example, in city water or in particle-free water and have nothing to react with, typically they foul any membrane within shortest time. But also from experience, as soon as they are combined in a flock or have reacted with particles and have also been in touch with coagulant, for example, it is absolutely neutral to the membrane. Of course, there's always a slight risk actually that this polymers getting redissolved and then foul the membrane. So therefore, it is definitely needs to be taken carefully. But you know, our technology is also in the effluent of dissolved air flotations and clarifier, which continuously operating by addition of flocculants. So it's, I would say, not impossible, but it needs further investigations actually.
Thanks, Patrick. There's one question about the SEC of ceramic membranes compared to polymeric membranes. I'm not sure if I fully understand the question, but I think it's related to OpEx and energy. And I think we addressed that. Just want to make sure we covered it. Then can we also have a comparison of the cost of ceramic membranes and polymeric membranes? I think we touched on this earlier. What was your water recovery percent in normal desalination stage, so pre-treatment? What's our water recovery and what is your salt rejection and energy use?
Okay, so the recovery in seawater, I mean, also here it depends a bit on if there is where the intake is located and so on. But generally speaking, we always reach more than 95% recovery rate in a seawater application without further pre-treatment like clarifier or dissolved air filtration. What is typically in other technologies, salt rejection is actually zero. Yeah, all salt is going through the filter. It's a pure mechanical filtration process, so only particles are rejected. Energy usage is in a range of, I would say, below 20 watt per cubic meter of water. So we only use the backwash and we have aeration only during the backwash, which happens every 3 hours or so. So it's really compared to the hour, of course, you know, absolutely at the lower end and comparable maybe also to pressurized in-out filtration processes. So nothing special here, but typically below 20 watt per cubic meter.
Thanks, Patrick. Can you comment on the presence of slimy compounds in the wastewater and its impact on the clogging behavior of the membranes, assuming this is backwash wastewater?
Okay, we don't like slimy stuff, actually, that's for sure. Of course, you know, it's always, you know, we have to talk about maybe algae is creating some polymers as well, which result most likely in a slimy compound. But we need then to talk more specific what you're targeting. What is the source of the slime actually? And of course, it's I think with coagulation and maybe with other substances like we have, as I introduced before, with bentonite and other supports in the pre-treatment, we can help to prevent the membrane from those slimy substances. That these slimy substances will then be attached to the layer which we create on the membrane. But of course, if this slime is hitting the membranes, we need then most likely chemical cleaning. Now that's all membranes are the same here. But as I said, you know, we have processes maybe to help and to support a stable operation and to prevent the membranes from fouling.
I think the basic principle is, so what makes CERAFILTEC unique in a way is that we're trying to look at every project. How do we create the best solution? using ceramic membranes, right? And that sometimes includes process optimization, playing with coagulants, using bentonite, as Patrick mentioned. And then the key differentiator for ceramic is that this slimy content is probably messing with all filtration systems. And the differentiator with ceramic is that you, without limitations, can clean the membranes, right? And that's, I think, the key benefit, especially also for industrial applications. Next question, when integrated with a conventional water treatment plant treating turbid river water, what the use of organic flocculants at the plant have any impact on the filter cycle of the recovery plant?
Yeah, maybe we talked about already about flocculants, which are organic polymers. Actually, there is a risk that they also foul the membrane. So, you know what the good thing is what we can offer. We have lab scale. We call them suitcase units. So it's always good to test actually if there is still free polymer in the water which can foul the membrane, and if this is the case, it is always the question, you know, if we can add maybe additional coagulant to neutralize then the flocculant. So there is always a possibility actually to cover that. I would not blindly go into the design and just design with a lot of guesses and hopes. I would maybe furthermore recommend to test beforehand and then find the right solution.
Thanks. Next question. What are the standard characteristics of the membrane, like pore size, MWCO, porosity, and size of the membrane plate? I think we can just point them to our website. Honestly, I think all of the specs are listed there, point size 0.1 micron, and then all the sizing is listed on CERAFILTEC.com.
Yeah, molecular weight cutoff is also like a polymeric membrane, 100 kilodalton porosity. I don't have in mind right now. And the size of the membrane plate, oh my God. I mean, for me, it's always important. They have 6 square meter per module. It is something like 60 times, I don't know, 30 something centimeters. But you can find a detailed description here too.
All on the website.
Yeah.
Is it should the membrane be changed annually, or what is the replacement frequency of the membrane?
That would be a great business for us, actually. So please give me a call. we get into the business now. It will be not changed. As we mentioned, you know, we expect a lifetime of 20 years currently.
Yeah. Is the material of the ceramic module the same for backwash as for MBR?
Yes, it's the same. As it is the best for all applications, actually. Yeah, no matter what.
Yeah. Do you have any references using the ceramic UF membrane as pre-treatment in desalination?
Oh yes, we have. Currently, just I think 1 year in operation now in Northern Africa. We have a 140 MLD plant, which is working under really challenging seawater conditions with a high TOC of up to 12 milligrams per liter. Algae concentration as chlorophyll in the range of 40 micrograms per liter, actually. No pre-treatment and a very poor intake. So the intake is just like, you know, throwing a 1,000 millimeter pipe in the sea directly into the surf. So the plant is operating very successful as pre-treatment to RO, and also through periods where there is in parallel, there's a sand filtration unit feeding another RO system, often has to switch off as to the high turbidity. Our system is running 24/7.
Excellent. And then last question here in the chat, how does the pre-treatment quality compare to PES UFs with a smaller pore size for RO pre-treatment applications?
Also very good question, actually. And I think, you know, what we have experienced so far, that due to the fact that we have no fiber breakages, that means the filtrate quality is really always in shape, means turbidity is in the same range than from a polymeric membrane, which has smaller pore sizes. As you know, the particle size, particle removal rate is the same as the particle size is defined as 400 nanometer, actually. So everything below or above 400 nanometer is considered as a particle. Below it is dissolved. So therefore, we're removing all particles. So that's why this quality parameter is the same then for the polymeric membranes, except the fact that also after 10 or 20 years, our membranes will produce then without fiber breakage. So for me, it doesn't make sense to have a 100% barrier for particles if you consider 1% fiber breakage per module of the capillaries. Yeah? That doesn't make sense to me.
I think we can also build on this on nsf.org. You see the log removal details of all the polymeric membranes for the American standards, and the CERAFILTEC solution actually has a higher LRV removal in the NSF 419 tests as 0.02 micron polymeric membranes. Maybe that's also a fact and publicly available that we can lean on.
Also, most likely when you talk about RO pretreatment, you always need to talk about SDI, which is a really poor parameter. But nevertheless, you know, we have in competitive tests, also the SDI was always below 3 actually. It depends, of course, also on the dissolved organics which go through the polymeric UF or through the ceramic UF, and depending strongly then on the coagulation which is applied in the pre-treatment to the UF, right? So this all comes together. But I would say, generally speaking, the membrane as such has the same rejection rate and the same quality for the RO. And in the end, it is better because it is more reliable and more robust.
Wonderful. This concludes all of the questions. Patrick and I will stay here for a few more minutes. We'll turn off our cameras. Feel free to, for any last minute questions, type them in here. We are available. And you know, you can reach us at webinar@cerafiltec.com anytime. Thank you so much, everyone, for joining and for supporting this exciting journey on not just with CERAFILTEC, but really being passionate about innovation in the water sector. It is so desperately needed. Thank you, everyone.
Thank you very much. See you.